Hello, my name is Joseph Albro, and I'm an undergraduate researcher from the University of Pittsburgh and a member of Dr. Jeremy Levy's research group. Before I begin, I would like to thank the funding that has made this research possible. In this video, I will be talking to you about the cryogenic force microscopy of sketched lanthanum aluminate tritium titanate nanostructures. So the material that we primarily work with in our group is the lanthanum aluminate tritium titanate heterostructure, also known as LaOSTO. It exhibits many interesting properties, including a high mobility, two-dimensional electron gas, a metal-to-insulator transition with a critical thickness of 4 unit cells, superconductivity, magnetism, tunable spin-orbit coupling, and many other interesting properties that I did not have room for here. So the properties of LaOSTO that I just mentioned are all two-dimensional properties. By using a conductive AFM lithography technique that we created in our group, we can confine these two-dimensional properties to one-dimensional nanowires, which allow us to create electronic devices which provide us with further insight into the physics behind LaOSTO. This technique starts at the sample growth stage, where we only grow just under the critical thickness of LaO on top of bulk STO. This means that the sample is initially insulating. Then we place contacts at their interface so that way we may directly take measurements of what is happening at the interface. The conductive AFM part starts by bringing a conductive atomic force microscope tip in contact with the sample. Then, by applying a positive bias with respect to the sample, we can deposit protons on the surface which correspond to electrons at the interface. By dragging the tip along the surface, we can create nanowires which are as small as 2 nanometers wide. We can reverse this process by applying a negative bias with respect to the sample, thus removing the protons from the surface and creating a barrier at the interface. This is important for 2 reasons, the first being that if we make a mistake, we can erase the structures on the surface and start over again, allowing for rapid reconfiguration of our devices, and secondly, we could create more intricate structures such as single electron transistors or field effect transistors. Like I just mentioned, conductive AFM lithography allows us to create devices such as sketched field effect transistors, single electron transistors, and study interesting properties of LaOSTO, such as anomalous high mobility at room temperature, non-local transport, Fabry-Perot interference, and create reconfigurable superconducting nanoelectronics. Just like the nanostructures we write confine 2D properties to one dimension and provide us with insight into the physics of lanthanum aluminate tritium titanate, using local probes can provide additional information into the properties of the materials that we study. For example, previous research using local probes, in this case scanning squid microscopy, has revealed enhanced transport in the direction of the domain walls of strontium titanate, which form when strontium titanate undergoes a cubic to tetragonal transition at 105 Kelvin. As you can see in this image here, they're able to repeat this experiment many times by cycling the temperature to above 105 Kelvin and performing the experiment again as shown. So here you have the current density, which is increased in the direction of the domain walls. And they were also able to perform this experiment on another sample and show that the current density is enhanced along the 100 direction of this particular sample. Another group has used local probes to reveal properties that would not have been seen in bulk measurements. Using scanning single electron transistor microscopy or scanning set microscopy, they were able to provide not only a map of the tetragonal domains like scanning squid microscopy, but also the orientation of the domains in strontium titanate, as you can see here. Our group has already used local probes to non-destructively image the carrier density by exploiting the reverse piezoelectric effect. So previously, the way we would image the width of the nanowires that we create using the conductive AFM lithography technique I previously mentioned would be to apply a negative bias to the tip with respect to the sample, and then essentially draw or erase one of our nanowires while monitoring the conductance through that nanowire as a function of tip position. However, this essentially destroys our nanowires. Instead, we could apply an AC current through the nanowire, and by placing the tip in contact with the surface, and measuring the changing tip deflection as a function of position, since the sample will be expanding and contracting due to the reverse piezoelectric effect, we can measure the carrier density without destroying our devices shown here. So in the red areas, the tip will be deflected up and down less than in the green areas. On the flip side of this, one could locally apply pressure and measure the change in voltage under constant current. Since strontium titanate can be gated by locally applying force to the domain walls, one could provide a map of the tetragonal domains by simply pressing into the surface and monitoring the change in voltage when the sample is under constant current. As you can see here, so these are the twin domain walls that are shown by using cryogenic force microscopy. One experiment that we would like to perform is room temperature voltage gating of a device that we write onto the surface using inductive AFM lithography. So here we have a field effect transistor, for example, and by changing the tip bias with a function generator, which is wired into the reference of a lock-in amplifier, we can measure the change in the drain current at the frequency of the function generator as a function of the tip position, which we then plot from the lock-in amplifier using the atomic force microscope controller as a function of the tip position. So we have a function generator. We're measuring the change in drain current of a device that's being run at a constant excitation voltage, and the tip is changing at some rapid frequency, tip biases. So here we drew a field effect transistor which starts out as a T-junction, and then we erase the connection of the T. So this using a negative bias, so this creates a source, a drain, and a gate. And by applying a 10 volt AC bias to the tip and scanning over the device in contact mode, we can see that there is a change in the conductance as we scanned over the junction of the field effect transistor. So a similar experiment to the one I just showed, we'd also like to drive the tip into the sample, locally applying force to where the sample is. So the way this experiment works is the function generator, instead of changing the tip bias, is driving the piezoelectric drive element. It's also acting as a reference for the lock-in amplifier. We measure the drain current at the frequency of the reference of the function generator, and then we plot that as a function of the tip position. So here you can see that we created a two-terminal device. So essentially the way that works is we have a wire, and then we cut the wire using a negative bias, so we have a source and a drain. The tip is driven mechanically using an AC signal from the function generator, which is applied to the piezoelectric drive element. In this case, the tip bias is not changing so that we don't accidentally force gate the sample. Once again, we're applying the drain current of the device as a function of tip position. So you can see here there's a change in the drain current as we scanned over the junction of the device. So the results that I just showed were taken at room temperature. However, we'd like to still perform these these experiments at low temperatures, since strontium titanate undergoes the cubic to tetragonal transition at 105 Kelvin, and many other interesting properties come about at only low temperatures that are not seen at room temperature. So in order to perform these low temperature measurements, we have to have a low temperature atomic force microscope. So we started with a vacuum atomic force microscope and upgraded it to a cold temperature system. Originally, we used a pulse tube. However, we found that this introduced too much mechanical noise, which was not conducive to performing scanning probe microscopy. Also, it didn't have the cooling power that we desired, so this past summer, we decided to upgrade from the pulse tube to a helium flow cryostat, which should be able to solve the two issues. However, since you can see the two vary in size, stature, so the way they're basically held up, and the orientation. So this one is like vertical, and this one will be sticking in horizontal. So I had to essentially design a way to use a helium flow cryostat with the existing vacuum atomic force microscope setup. So what I came up with is essentially a clamp made of solid aluminum set on rails that allows to clamp the AFM securely in place. This is useful for not only just holding the cryostat in place, but also, since it's on rails, we could bring it back and perform maintenance or wiring, etc. So also there is a lot of programming involved in this, so there's a lot of different moving parts, so I need to create a program that would tie those all in together and also allow us to do what we wanted to with the system. So essentially I've created a program very similar to the one seen here that I created for another atomic force microscope in our lab that will do just that for us. So here are the results of the hardware part of the upgrade. So you can see here we have basically essentially a big block of aluminum sitting on two rails that allow us to move back and forth, and so here's the vacuum chamber. We have bellows to help reduce vibrations, and here's the cryostat, which is connected to the atomic force microscope by using a flexible link which actually cools the sample instead of the actual AFM head by cooling a piece of copper below the sample, which is in thermal contact with the sample itself. So the atomic force microscope head is actually located directly above the chip carrier which holds our sample, which is then cooled by the cryostat, which helps remove the headaches of actually cooling the entire atomic force microscope head to low temperatures. So in summary, conductive AFM lithography allows for the creation of reconfigurable oxide nanostructures. Local probes offer unique insight into the physics of lanthanum, aluminate, strontium titanate that are not revealed by bulk measurements. And I also proposed a method of cryogenic force microscopy at low temperatures using a modified vacuum atomic force microscope. So thank you.